In the previous lesson, we looked at the basics of Unity's physics engine, which pretty much centers around these different aspects. Rigid bodies via the attached rigid body component, colliders via the collider component, collision layers to determine what colliders collide with each other, and controlling physics behavior using FixedUpdate. Out of all of these concepts, the least intuitive, and the one we spent the least time understanding, was how FixedUpdate works. Particularly of interest is what code belongs in FixedUpdate versus in update. So in this lesson, I'm going to spend much of the time explaining the important differences between FixedUpdate and update, and the simple rules of thumb to follow when choosing which one to use, and how to get them to sort of play nice with one another. Right, so what do we know about FixedUpdate? Once again, it runs just like the normal update method, so in a loop-like pattern, except FixedUpdate runs on a fixed time interval, running every 0.02 seconds. So basically 50 frames per second, right? So if the game runs at, say, a steady 60 frames per second, we know that we'll have 60 updates, and we'll have 50 fixed updates within that second. If it runs at 30 frames per second, then we'll have, once again, 50 fixed updates, but we'll have 30 updates within that second. Now to see the progression of how updates and fixed updates are called, just attach a simple script to a game object, and in the script have the debug log output update, in quotes, in the update method, while the debug log outputs FixedUpdate, in quotes, in the FixedUpdate method. Then run the game and watch the console to see the pattern of update versus FixedUpdate calls. Then simply change the FPS, the frame rate, with the application settings to see how this changes the pattern, making for more updates than fixed updates at 60 frames per second, or less updates than fixed updates at 30 frames per second, for example. So let's take a closer look at the resulting pattern that you get when you do this, that you'll see in the console. How do we think about this sequence of fixed update and update? Intuitively, you might just picture it as a continuous stream that eventually ends up, out of sync at some point. But what ends up happening when the frame rate remains steady is that you get this looping pattern within the broader loop, rather than a continuous stream where you would probably picture not much of a pattern occurring due to the ever-changing difference in time interval between update and fixed update calls. And I think studying this looping pattern a bit will give you some insight on how update versus fixed update run alongside each other. One of the most obvious features of the pattern that gets produced is that there's an unevenness between the update and fixed update calls. Depending on the frequency of update calls, you might get one fixed update between update calls, or you could get a bunch of fixed updates between update calls, or you can even get no fixed update calls between update calls in the case of the game running at 60 frames per second. So running our test script at 60 frames per second, let's then match up what we see output to the console with a visualization for it. When the game first runs, you'll briefly see a bunch of fixed updates run one after the other. And then the engine will sort of settle into a looping pattern that we've been talking about. The pattern seen here, when the game is running at a steady 60 frames per second, is particularly demarcated by the point where we have two updates run one after the other, and no fixed update in between. The pattern then starts again, once again like a loop within a loop, so put aside the visualization of a continuous stream where it's kind of hard to imagine the relationship between updates and fixed updates and where it all ends up exactly, and instead visualize the pattern with this sort of loop within the loop behavior as something like this. Note that the precise time intervals between update and fixed update are not really accurately visually represented here, as it's difficult to represent and not really important for the general point being made. So with this pattern being produced, we see that there is some regularity despite the differences between update and fixed update, even at lower frame rates. In other words, we typically get at least one fixed update after every update. sometimes more if the frame rate is lower. So you maybe get the sense that updates and fixed updates aren't wildly out of sync, but nonetheless you might think that any irregularity between the two is a big problem. In other words, if we can't accurately predict how many fixed updates run between updates if the frame rates are changing, how do we create a world that appears predictable and deterministic and running in sync? Well, here's why the difference of more or less fixed updates between updates doesn't matter. It doesn't matter as long as fixed update is only used to make physics calculations. I'm going to repeat this because the point is crucial. It doesn't matter if you have 2 fixed updates between update calls or 20 fixed updates between update calls, as long as you're only putting physics calculations in fixed update. That's because the way that physics is calculated over time doesn't change with more or less intervals used to make those calculations. It's kind of like, say, calculating how far your car has traveled. It doesn't matter if you use meters or kilometers. Meters offers a more accurate measurement because its intervals are more frequent than that of kilometers, but doesn't change the fact of how far the car traveled given its velocity over time. The reason for this is because there's a backdrop in the real world, I'm talking now, of fixed time progression. Time, in other words, doesn't meaningfully change. Einsteinian relativity notwithstanding for you fellow science geeks out there. But that aside, if the velocity over span time is all that determines where the car should be, and it's all the same otherwise, whether or not you're using meters or kilometers to measure the exact place that the car would be. So my analogy may or may not be one-to-one, but that's kind of how you can think about fixed update. More fixed updates only makes for more precise or smoother physics calculation, right? So this is why we use fixed updates for calculating physics changes. It offers a fixed time step, which models that backdrop of linear time in the real world. So in many ways, fixed update works in the opposite way than we've come to learn that update works. We use tricks like time.delta time in update to make the update loop appear deterministic. By deterministic, I mean objects following a predictable movement and behavior pattern, regardless of the amount of updates. So there's constant time in the background, the sense of that. And that's basically just a nifty illusion. Whereas in fixed update and working with physics calculations, we're not just creating the appearance, but actually modeling the underlying forces that create that appearance. Would it make sense in this modeling to use something like delta time, like we did in update, increasing an object's velocity, for instance, when the frame rate lowers? Of course not. What force in nature would logically explain that additional velocity? If anything, you would expect the opposite, that the object would appear to slow down if the time scale were to slow down. So that's why fixed update operates as a steady, sort of like a steady beat of a drum in a song. No steady beat, no song. So no fixed time interval, no physics modeling. Science needs fixed intervals. A ruler isn't a ruler unless the spaces between the units of measurement are consistent. Okay, I think I'm probably done beating that point home of why fixed update needs to be a constant time interval. So actually implicit in all this is that the frequency of that interval, it can be faster or slower, and that frequency can be set in the project settings time dialog, but it's best to just leave that alone. It's kind of optimal for processing and whatnot, and for our purposes at every 0.02 seconds. So anything in code that changes a value of a physics object, velocity, force, etc., are all that goes into fixed update. We'll demonstrate all this a little more later, but just keep in mind as the first rule, physics stuff in fixed update, non-physics stuff in update. I'll also go into more in depth into what constitutes physics stuff versus non-physics stuff in a bit, but sometimes the distinction is a bit blurry. For example, what if you have user input that is used to determine a physics calculation, like pressing a button to make the player move, for example? User input is definitely non-physics code, so it should belong in update. But the physics stuff that ends up happening due to that user input, for example, increasing the rigid body velocity, definitely does belong in fixed update. This is probably the trickiest sort of interplay between the two methods that you'll come across, and thankfully it's not too difficult to bridge this gap. So let's see what happens when we put the user input along with the physics calculation. It sets off all in fixed update. Here we're using user input to determine whether or not a force is applied. The trouble is that inputs are pulled in the background at the frame rate that the game is running at, not the fixed time step of fixed update. So in other words, you can think of it as inputs being read at the same rate as update cycles. So if the game is running at 60 frames per second, we'll get a dropped input in the case where we saw earlier where there's no fixed update between the two updates. We saw that that's actually pretty often. In fact, at 60 frames per second, roughly between every 5th and 6th update call within that looping pattern that we saw earlier. So picture it this way. If your input is read on the 5th update, it will only be true for that update cycle, since get key down only returns true on that frame that the input was read. And on the next update cycle, it'll become false. And then when the next fixed update runs, it will then catch that input and it'll read it as false. Now, if the game is running at 30 frames per second, this problem probably won't occur because there should always be a fixed update run after every update, since fixed will run more frequently than update. But this is still a problem because, as we saw, it's difficult to guarantee a steady frame rate because that's platform specific. Frame rates ultimately depend on the power of the underlying platform, so that can't always be guaranteed. So to combat this, you might want to set something like a flag, a state in other words, for inputs that were read in update, and that fixed update will later act upon, something like this. But here again, we have the same problem as we had before. If the game is running at 60 frames per second, then we still have the same issue of dropped inputs because of there being no fixed update between every 5th and 6th update frame. In this case, upForce flag will be flipped to false after every 6th update and will result in fixed update not applying the force. But now we have a problem even at lower frames per second. Since we have 2 fixed update cycles between some update cycles at 30 frames per second, for example, and even more at lower frames per second, the force gets applied twice in those instances. This would result in a higher or a lower jump depending on how many fixed updates were called between updates. So the solution to this is to use update to set the flag to true, and then use fixed update to set the flag to false as soon as it's been detected by fixed update. This has the effect of sort of caching or storing the input state across successive update cycles if fixed update doesn't occur between those cycles. All right, so now that I've shown you the most tricky scenario probably of handling the interplay between update and fixed update, usually when handling user inputs that have an effect on physics, and you now know to keep physics stuff in fixed update and non-physics stuff in update, the obvious question at this point is, what exactly constitutes physics stuff? How do you know what is calculated using the physics engine and what's not? Well, basically anything to do with affecting a rigid body is a physics calculation, particularly if it occurs continuously over a series of frames. There are a few cases where you're not really calculating anything, you're just sort of setting a physics value, such as making an object grind to a halt on a single frame, say by making its velocity 0. In that case, it's probably okay to do that in update. There isn't anything being calculated over successive frames, so that's probably okay. Okay, that was a bit of a mouthful. I don't mean for this lesson to scare you off. That's the last thing I would want, is for you to sort of walk away from this thinking, all this just sounds way too overcomplicated to bother with. In some ways, it probably sounds a lot more difficult than it is in practice. When you actually start to work with the physics engine and see the results on your screen, I find that intuition kind of takes over and it should make a lot more sense. So please stick with me in the next few lessons, and I think you'll find that the trade-off is worth it. You'll see that you end up getting a lot of really cool functionality that would otherwise be very complicated without using the physics engine, in exchange for just being a bit more careful with how you use FixedUpdate, and maybe not always understanding how this magic is happening under the hood. Magic of all these modeled physics calculations occurring in some black box somewhere deep in Unity. And ultimately, you can make so many cool things happen with such little code that it's just too tempting to ignore the physics stuff. In the end, all this stuff kind of seems like magic, how Unity gets it all working, and you don't really have to think of all that much from all these different angles, and just kind of go with your intuition and have fun in the process. And honestly, most of the time, if you come across a bug, all you have to do is see if your game is working at 60 frames per second and 30 frames per second. If there are bugs or any major differences between these two extremes, you sort of, at that point, would want to sort out that bug. But otherwise, if it all works, which it often does without it being obvious why it's working, don't sweat it. You know, Unity does a good job of keeping things running, even if you don't understand it all. So that's about it for the primer on physics and FixedUpdate. For our part, we already looked at probably the biggest gotchas with the physics engine. And in the next lesson, we'll start rapidly developing our game using these new concepts. I'll see you there.